First order reaction. We generally represent a first order reaction as A giving product. And the rate of that reaction R can be written as decrease in concentration of A with time minus dA by dt. You can represent the concentration of A as dCA. CA is the concentration of A by dt. You can use any one of this equation, and you can also express the rate as rate is directly proportional to concentration of A or CA, or rate is equal to a constant K1. Since it is the first order reaction, we use the subscript K1 into concentration of A. Hereafter, we are using CA to represent the concentration of A. This is equation number 2, and from 1 and 2, we can write minus dCA by dt is equal to K1 into concentration of A. In order to find out the variation of concentration with time, you have to integrate this expression, and for integration, in order to perform the integration, you have to separate the variable. That means you have to bring the concentration terms on one side and the time on the other side. That means you just rearrange this equation like this: dCA by CA. Here the concentration terms are on the left hand side, and bring the time term to the right hand side. K1, this is a constant, into dt, and before performing the integration, you have to fix the limits of integration. And in order to fix the limits of integration, let the initial concentration, that means at t is equal to 0, the initial concentration of A is taken as C0, and at any time t, the concentration is taken as C. And these are the limits of integration. This is the lower limit and this is the upper limit. Okay, then perform the integration. You just put integration sign on the left and right of equation C and write the limits: minus integral C0 to C dCA by C A is equal to K1 into integral 0 to T dt. dCA by CA, 1 by CA dCA, the integral of 1 by CA is ln CA, and therefore your after integration ln CA minus sign is there, and you just apply the put the limits. Again, integral dt is t. Again, put the limits 0 and t there, and expand it or apply the limits: minus ln c minus ln c0 is equal to K1 into t minus 0, or minus ln c plus ln c0 is equal to K1 into t. This is of the form ln A by B, ln A, ln B. ln A minus ln B can be written as ln A by B, C0 by C. ln C0 by C is equal to K1 into T. Or rearrange the equation: K1 is equal to 1 by T ln C0 by C. Converting to base 10 logarithm, you just multiply this equation by 2.303 and convert ln to log. That is K1 is equal to 2.303 L log C0 by C. This is one way of representing the equation for rate constant for the first order reaction. Let A be the initial concentration and X be the amount reacted at time T. Then A minus X gives the concentration of reactant after time T. That is, in the above equation, instead of C0, that means the initial concentration, you can replace C0 by A, and C is the amount, concentration after a time T. Here, X is the amount reacted. Therefore, after a time T, the concentration of the reactant left is A minus X. Therefore, instead of C, you can write A minus X. Then your above equation becomes K1 is equal to 2.303 by T log A by A minus X. Log A by A. This is another way of representing the equation for the rate constant for a first order reaction. Diagrammatically, you can represent the rate of first order reaction